So today we will continue with the chapter 9 review. Last time we went over what the definition of an acid and a base. You know, acids are proton donor, bases are proton acceptors. When you have an acid and it donates its proton, then it becomes the conjugate base of that acid. When a base accepts a proton, it becomes the conjugate acid for that base. Water is what we call an amphoteric substance, which means it can be an acid or a base. It can act as both. We saw how to classify, you know, different acids in the strengths of the acids, and it's the same classification as what you do for strong electrolyte versus weak electrolyte. A strong acid is a strong electrolyte, which means the arrow of its dissociation, when you are writing the dissociation of the acid in water, like in this equation here, the arrow would be a single arrow to the right, a straight arrow to the right, and it's a complete reaction, which means the acid completely dissociates in water to give ions, so the conjugate base, you know, A minus, and then the hydronium ion. And so that would be a strong acid if you have just one single arrow to the right. And when you have a weak acid, you have those double arrows. And here it's really a computer one. I don't like it. It's not really how we do them. It's more like one arrow to the right, and below that, parallel to it, one arrow to the left. And so these double arrows indicates reversible reactions, which means it's like an equilibrium. And both reactions happen, the forward reaction and the reverse reaction. And a weak acid will have that kind of arrow, which shows that actually the acid only partially dissociates into its ions. And because it only partially dissociates, you have a small proportion of ions. And typically the acid, you know, the HA here, you know, the left side will be favored. And you have a lot of undissociated acid that is typically a neutral molecule. And you will have very few ions. That's why it's a weak electrolyte. It's weakly conducting electricity. This reaction is also good to see how we classify, you know, the reactant of an acid dissociation, for example, here, as the acid, the base, and then the acid becomes the conjugate base, and the base becomes the conjugate acid. So you need to be able to name, you know, what the function of each, you know, reactant and product. And then we wrote another acid dissociation reaction here. That's acetic acid. Acetic acid is particular because it can be its formula can be written many ways. And this way of writing it shows how this hydrogen, the first in the formula, is the acidic hydrogen, the one that will be donated when the acid donates its proton. And then you have the acetate ion. But it's also written as a CH3COOH. And in that case, then the H to the right would be the acidic hydrogen. So if you count the number of carbons and hydrogens, you know, it's still the same number, but the way the formula is written can be disturbing, because then you don't recognize it. Anyway, so we learned in chapter 6 how to write equilibrium constant. And for an acid dissociation reaction, we can write an equilibrium constant that will be then called an acid dissociation constant, because it's referring to that acid dissociation reaction. So it's the concentration of product over concentration of reactant. And remember how we are not writing solids and liquids in the equilibrium constant, because their concentrations are constant, so they are kind of included into the value of K. Then we know how to plug in the values if we are equilibrium concentrations. We know how to, so given the Ka value, this can also help us decide if we have a strong acid or a weak acid. And here, when the Ka is very small, because here 10 to the negative 5 means you are dividing 1.8 5 times by 10, so it's a very small number, very small, which means if you look at this formula here, if this is very, very small, much smaller than 1, then that means the concentration of the reactant is much greater than the concentration of product, right? And that means the equilibrium is favoring the reactant. And if the equilibrium is favoring the reactant, then that tells you this is more abundant in the reaction vessel. And that means you have very few ions here. And so it's a weak electrolyte and also a weak acid. So partially dissociates. And so that's a weak acid. Okay, we learned how to calculate the pH of a solution given the hydronium ion concentration. For this, you will use this formula. pH equals negative log of the concentration of the hydronium ion. pH has no units. So what is tricky with pH is the number of decimal places you should keep. So for pH, we only look at decimal places, and this number of decimal places should match the number of significant figures in the reaction, in the, sorry, concentration. So sometimes that may be the trickiest thing to do. And then when you have a pH below 7, it's acidic. pH above 7 is basic. When you need the hydroxide ion concentration, you use the Kw, which is the ion product formula for water. W is for water. Kw is actually the equilibrium constant of the dissociation of water into those two ions. And so because you have water as reactant, it's not showing up in the equilibrium constant. So that's why the equilibrium constant of the dissociation of water is just those two ions that are formed, that are the product, multiplied together. And so and it happens that this value is always true for all aqueous solutions at a given temperature. It's 25 degrees Celsius. And so when you know one of the concentration, let's say for example H3O plus, then you can find OH minus because Kw is a known value. It's 1.010 to the negative 14. And so when you know the concentration of the hydronium ion concentration, you put it in the denominator, Kw over H3O plus, and that's going to be your hydroxide ion concentration, hydroxide. So we were arrived there. And let me just say that these formulas are in your reference. They are page 5 of the reference packet. So if you go to page 5, that's where you have everything for chapter 9 and acids and bases. And so this table can be useful if you want to know if you have a strong acid or a weak acid. So strong acid on top, weak acid on the bottom. And here you have the formulas for the pH calculations, the ion product constant of water, and it reminds you how to do for the sig figs. You know, the concentration should have the same number of sig figs as there are decimal places in the pH. So, and here that's a roadmap. So for example, people sometimes are confused about which formula to use. And so it shows you that, for example, if you have the hydroxide OH minus ion concentration to the left here, and you want to calculate the hydronium H3O plus, Then you follow the arrow that goes from the hydroxide to the hydronium, and it's going to be the Kw over OH minus, right? Because OH minus is known. If you want the reverse, if you know H3O plus and you want OH minus, then you do Kw over H3O plus. And for the pH, so for the pH, you have to know the hydronium ion concentration, otherwise you cannot calculate the pH. And the pH, so you follow the arrow that goes from the hydronium ion concentration to the pH, and the pH is equal to negative log of the hydronium ion concentration. And if you know the pH, you want to retrieve the concentration of H3O plus, then it's 10 to the negative pH. Don't forget the negative sign, because it will give you a value, but it's going to be a huge value, and it's totally wrong. Concentration of hydroxide ion and hydronium ion should always be with negative exponent, typically with scientific notation, and the exponent should be negative. So let's continue with the review, and we were arrived here at this question: can this acid-base conjugate pair act as a buffer? And this refers to the acetic acid here. Acetic acid, acetate. Can this acid base pair, because acetic acid is the acid, the acetate ion is the conjugate base. So can these two together make a buffer? So I would like you to tell me yes or no in the chat. And we'll say why it can or it cannot. So tell me yes or no. Can acetic acid and acetate make a buffer? Yes. So let me remind you, what is a buffer made of? Let me change that color. Blue. A buffer is made of a weak acid and its conjugate base. It's made of a weak acid. Every word counts. Weak is essential. It has to be a weak acid, and it has to be its conjugate base. So do we have a weak acid and its conjugate base here? So those who have not answered, you can answer now. So yes, this can be a buffer. Acetic acid and the acetate ions are a weak acid and yeah, acetic acid is a weak acid, I should say. Acetic acid is a weak acid and the acetate ion is its conjugate base. So yes, these two can form a buffer. Of course, to make a buffer, you would have to have large amounts of both. So you can see here when you are putting acetic acid in water, it's partially dissociating, which means, and typically when you look at the Ka value here, it indicates we have a lot more reactant than product. So that means you are producing very little of the acetate. So that's why when you have when you really want a buffer, you have to make a mixture of acetic acid that will provide the acetic acid in large amounts because it's a weak acid and it stays as an acid. It doesn't dissociate much. So make a mixture of acetic acid and add a salt, an acetate salt. acetate salt to it, like Na, C2H3O2. NaC2H3O2 is the acetate ion. One negative charge will be cancelled by the one positive charge from the Na+. And so that's what we call a salt of acetate, right? An acetate salt. We call it a salt because it's now combined with a metal, and so that makes it an ionic compound. And ionic compounds are typically salts, which means they are crystals. You know, this would be like a crystal that looks like very much like a salt, you know, table salt, I mean. So sodium acetate, you would add some of it to the acetic acid solution, and that would make a buffer. And you want the amount of acetate and acetic acid to be equivalent, same amount and large amounts. So why do we need both? It's because when you have the role of a buffer is to maintain the pH. And these two, I think the pH would be around 5 or smaller. And they can maintain the pH as long as what you add, you know, the acid you add to it or the base you add to it are not too much, right? Buffers have what we call a capacity to hold or maintain the pH at the value they are supposed to, as long as you don't disturb them with too much acid or too much base, right? If you put too much, then you will overwhelm them, and then we will exceed the buffer capacity, right? So you need large amounts of them so they can act as a buffer, and you need the acid and the base. The reason is because when you add an acid to a buffer, so when you add some acid, and any kind of acid that, you know, is a disturbance, you know, disturbing acid. When you add some acid to the buffer, so tell me, the acid will react with which part of the buffer? If you add an acid like HCl to this acetic acid acetate ion buffer, which compound will the acid you add react to? Will it react with the acid of the buffer or with the base? So will it react with the acetic acid or with the acetate ion if you add an acid to it? So tell me, acid or base of the buffer? Will the acid, yeah, will react with the base, right? Because you're adding an acid, so it's the base who will try to neutralize it, right? So when you add some acid to the buffer, the acetate base will react with it to, you know, to maintain the pH. Oh, you can't hear me? Oh no. Is it just for you, TJ, or others cannot hear me? Okay. TJ, it means it must be from you. Yeah, I'm not sure what to do. It must come from your own system. So when you add some acid, you know, that disturbs the buffer, it's the acetate base that will react with it to maintain Okay, that will maintain the pH. And if you add some base, disturbing base that, to the buffer, with what will it react? What will react to it so that it maintains the pH? When you add some base to the buffer, the base will react with, yes, the weak acid. The acetic acid will react with it to maintain the pH. And I should say, as long as the amount of disturbing acids or bases are small compared to the concentration of acetic acid and acetate ion, right? That's why you need large amounts of it and equal amounts. And so the pH will be maintained as long as the disturbing acids or bases you add are small compared to the acetic acid or acetate ion buffer. If you decide to make a buffer with it. So this question here is more like a chapter 6 review. If more of the acid is added to the reaction container, what will happen to the equilibrium? So let's go back. Maybe I'll copy that thing here. Copy that and put it back here. So we have this reaction. It's called acid dissociation because it's showing how when the acid is placed in water, how it dissociates into the acetate ion and the hydronium ion. And so it's an equilibrium. We have a double arrow here. And the question is asking, if you add more acid to the reaction container, add more acid, what will happen to the equilibrium? So it should make you think of a principle we learned in chapter 6. If you remember the name, it was called the Le Chatelier's principle. So, yeah, good. So I like to visualize those things, but so imagine like a big arrow, pointing towards the acetic acid. This is the acid, right? So a big arrow is like flowing the reaction vessel with a lot more acetic acid. So what the equilibrium will try to do is counteract the change. And the change here is addition of a lot of acid. So you are putting a lot more of this, and so the equilibrium will try to remove it because you're adding more. So the reflex of the equilibrium is try to remove that acetic acid that you're adding. To remove it, it has to go forward. If it goes forward, which means going from left to right, this will consume the acid, and you will remove it as at the same time that it is added to the reaction vessel. So yes, the equilibrium. So Le Chatelier's principle says that the equilibrium will try to counteract the change, or here I will specify the addition of acid, and will consume the acid by moving to the right. By moving to the right, it will consume the acid. By moving to the right and making more product from the acid and the water. So it's always this movement that tries to, so there is this flooding of acid, and so that pushes the equilibrium to the right, so that you are trying to, use that flow of acid and consume it. Okay, so we have another problem now. So do you have questions on what we just covered, buffers and Le Chatelier's principle, or? So we'll continue with the problem 5, which is something we've already covered, but more practice will be good. So given a solution with pH 11.65, answer the following questions. So first, is the solution acidic, basic, or neutral? So tell me, when you have a pH of 11.65, is the solution acidic, basic, or neutral? Yes. So pH allows you to classify solutions much more easily than the concentration of the hydronium ion or the hydroxide ion. Right? I saw that with the few of you who took the quiz. It's a lot easier to classify from the pH. So here pH is above 7, right? Above 7. So pH is above 7, so it is basic. pH above 7 is basic. pH below 7 is acidic. pH equal 7 exactly, it's neutral. So yes, this is basic. So what is the hydronium ion concentration? So for this, you will need to use, the reference. So let's look at the reference. We have the pH. We want the H3O plus concentration. So if we look here, so we have the pH. So pH is there to the right on the roadmap. We have the pH here on the right. We want the H3O plus concentration, and it shows with the arrow on top here that goes from pH to H3O plus. It shows that you need to use the formula that says 10 to the negative pH, or anti-log of negative pH. So make sure you have the negative sign there. Sometimes it's forgotten and it's really changing the value completely. So let me go back to this. So I'll write the formula here, and it says H H3 O plus H3O plus equals 10 and 10 to the negative pH. Right, that's the formula you want to use here. And so for the exam 3, there will be probably those formulas to be used, right? So please write the formula and then plug in the values. I need to see both. It's really a good habit to take. Always write the formula before you plug in the values. And usually, if you need to modify the formula, you always want to modify it before you plug in any values. It's a best practice. So here we have 10 to the, and the pH is negative, so negative pH 11.65. Okay, so maybe the trickiest is to do that on the calculator. If you have the TI30X2S, you do the second function of the log function. So the second, and then the log key is just below the second key. So you do second log, and it already opens times. So it shows 10 to the power of, open the parentheses. Then you do the negative sign that is between parentheses, next to the enter button. And 11.65, close the parentheses, enter. Okay. And if you have the TI84 plus, for example, or TI84 or TI83, it works for all of those. Yes, it's actually the same, except the log key is next to the 7-digit. So you do, so on that TI84 or TI83, second log, log key, which is to the left of the 7-digit. Negative sign again in parentheses, and then 11.65. And you don't need to close parentheses there. Enter. And so my answer is 2.2. I will put more digits than needed, but that's because I want you to think how we will run this. 10 to the negative 12. Please don't forget to report the exponential part of your numbers. I suspect some of you sometimes forget to show that in your answers. You have only the decimal part, and you forget to report the exponential part, which changes completely the value. So it's important to report both. So this is a concentration, the hydronium ion concentration. So it has a unit, and it's capital M for molar. It's a molarity, concentration in molarity. So now let's think about the, well, I'll do that after, because let's think about sig figs or decimal places. So we said earlier that for the pH, what matters are decimal places only. And here the pH has only 2 decimal places, right? 2 decimal places in the pH means you want to keep 2 sig figs in the concentration. So 2 sig figs means you will keep the 2.2. What comes after is a 3. So you round the 2 down, you keep it as a 2, and you drop everything after that, times 10 to the negative 12 again. Capital M for molar. Okay, so the concentration here would be that. Now I can change that to blue and black and bold. Okay. Are you all okay with the calculator, how to use the calculator? This is important to be able to do this. Okay, great. Super. So that would be the concentration. So there's a lot of details in this, just one line here, right? Don't forget the negative in front of the pH. Don't forget to report the, exponential part. Don't forget the unit. And, what matters in the pH are the decimal places, but then in the concentration, it's the sig figs. And vice versa, right? When you go from concentration to pH, that's still the same thing. So then next question, what is the hydroxide ion concentration? OH minus hydroxide ion. Okay, so again, you can look at the reference if you have it or your notes. So we have H3O plus. We have H3O plus. We want OH minus. And so for when it's about those two ions, you know, the ions that the water dissociates into, you want to use the ion product constant of water, the Kw. That's the formula you want to use. And when you have a concentration of one of the ion and you don't know the other, it's always Kw over the concentration of the other ion. So shouldn't be too complicated to, you cannot make mistakes, right? It's always Kw over the concentration of the ion that you know to calculate the ion you don't know. So here it's going to be, so I'll show where this comes from. You need to use the Kw formula, Kw equals H. Oh, let me take this. Times concentration of OH minus. Okay, but we cannot use it like that, right? We are looking for OH minus, and we know H3O plus, it's calculated above. So you divide both sides by H3O plus, and you get OH minus. Yeah. Equals, sorry. So Kw over H2O plus. The Kw value is known. It's 1.0 times 10 to the negative 14. All of this over the concentration of H3O plus, and that's the value we have here. 2.2 10 to the negative 12 equal. So here again, it can be tricky to do it on the calculator. So you want to use the EE key if you have one on your calculator. So in my TI30X2S, you would do so 1.0 if you want. The second function, and then the EE key is the X minus 1 key. So you see the capital E, negative sign 14. And by doing this, you don't need to use parentheses around it because the calculator knows it's one thing together when you use the E, capital E. Divided, and here again, you don't need parentheses if you use the EE key, but if you don't use the EE key, you have to open the parentheses here. So it's 2.2, second, EE key, negative 12, close the parentheses if you don't use the EE key, equals. It's important that you use the parentheses for the denominator if you don't use the EE key. Otherwise, your calculator may move the times 10 to the negative 12 to the numerator, and then you will end up with a times 10 to the, let me try this, 10 to the, no, doesn't like that. 10 to the negative 7, negative 27. If you if you don't put this in parentheses, and you don't use the E key, the calculator will move the times 10 to the negative 12 to the numerator, and then you would have an answer that is 10 to the negative 27, which is wrong. It's not the value. So let me get the proper value now. Negative 12. I prefer scientific notation here. So 4.5, 4.5, 4.5, etc. times 10 to the negative 3. Right, only negative 3. And that's capital M because it's a concentration. The hydroxide ion concentration is concentration in molarity. So here, the sig figs, it's the usual way. It's 2 sig figs in the Kw, 2 sig figs in the concentration of H3O+. So we'll keep 2 sig figs, which means we will keep the 4.5. What comes after the 5 is a 4, so we keep it a 5 times 10 to the negative 3 molar. Okay, so that would be the hydroxide ion concentration. So what I want you to notice is that whenever you have the concentration of the hydronium, so here 2.2 10 to the negative 12, right? And now the hydroxide ion, it's 4.5 10 to the negative 3. If you add those exponents, 10 to the negative 12 and 10 to the negative 3, so the 3 and the 12, that's 15 together, right? So negative 15. And that's telling you it's correct. It should be around 10 to the negative 14 because, it's not ones. The decimal places are, the decimal part is not 1. So then the exponent may be negative 13, negative 14, or negative 15 when you add those two exponents together. And here it's 15, okay? If you have something other than negative 13, negative 14, or negative 15, when you add those two exponents of those two concentrations, then it's wrong. Something is wrong, right? Because why? Because those two, when you multiply those two concentrations together, you get the Kw, and the Kw is 10 to the negative 14, right, when you multiply them together. So that's why those two exponents, when you add them, they should be close to 14. So they can be 13 or 15, but they should be close to 14. So that's a way for you to verify that it makes sense and it's, a value that makes sense. Do you have questions on that? So let's write the neutralization reaction of nitric acid when it reacts with calcium hydroxide. So neutralization reaction, there is a key word here. It's neutralization. It means it's that simple way of adding an acid and a base. So the form is that acid plus base gives, I will make just a simple arrow like that, gives water plus a salt. That's the general form of a neutralization reaction, okay? So that's what we want to do. So let's let's make a reaction like that with the acid, nitric acid, so HNO3. HNO3 is the nitric acid. It's an aqueous solution, which means it's the nitric acid in water. The base is calcium hydroxide, CaOH, and 2 times. There is 2 OH pair calcium. And that's also an aqueous solution. Let's give that an arrow. Okay, so I think it's easy here to know which one is the acid, which one is the base, because one of them has the name nitric acid. So you should see that this one is your acid, right? Because it has the hydrogen as first in the formula, so that's your acid. And here, hopefully, you recognize also that there is this OH in parentheses, which is the OH minus ion. It's that one above here, the hydroxide ion, right? And anything that has a lot of hydroxide ion is basic, right? A lot of hydroxide ions are making a solution basic. So that's your base, that's your acid. And those two, the H plus coming from HNO3 and the OH minus coming from, CaOH 2 times, are going to combine together and make water. So that's why this type of reaction has water as the product. And hopefully you see that when you do H plus plus OH minus, maybe I should write this here just to make things visual. H plus plus OH minus gives water. H2O comes from the fact that you add H plus, plus, and OH minus. And you can see the plus and the minus cancel, and then you end up with 2 hydrogens and one oxygen, and that's water. So that's why this H plus will combine with this OH minus to make water. Water, if you want to give a physical state, it's going to be liquid. Don't say it's aqueous. Water is either a gas, a solid, or liquid, but it's never aqueous, because aqueous means solution made of water as the solvent. And here it's water, your solvent, so it's the liquid. Okay, and that's why we have water. And then the salt. The salt here comes from the fact that you are combining the calcium ion, the positive ion here, with the negative ion that comes from the acid. So Ca, what kind of ion does it become when it's an ion? And for this, it's a predictable ion. So looking at the periodic table, you see that calcium is in group 2A. So it's going to be a 2 plus, right? So let me write calcium. Okay, I'll write 2 plus, but it will have to go away when you write the compound. So 2 plus. And I have to make it with NO3 NO3 negative 1. That's the nitrate. If you see here, when you have H plus, then NO3 has to be negative 1, right, to cancel the H plus. So that's the nitrate. And nitrate, if you can confirm that in your list of polyatomic ion, it's 1 negative charge, right? So together they will make a salt, an ionic compound, because we tend to call ionic compounds salt because they are crystalline solids. So here, the way to make them together a compound is by doing the crisscross trick, right? So the 2 from the 2 plus here will become a subscript for NO3, and the 1 here from the 1 negative charge will become a subscript for calcium. So calcium will become, and I will remove the charges, just calcium. I have to remove that. Calcium 1, because the NO3 has 1 negative charge. And then the NO3, I have to remove that, or just make it space. NO3, there will be two of them, right? Not here. There. NO3, we need a 2 because we said it's the 2 from the calcium 2 plus makes it a subscript for NO3, right? And so that's the formula of your salt. Calcium, NO3 2 times. Because you need 2 nitrates with 1 negative charge each. That's going to be 2 negative charges in total. We'll cancel the 2 plus from the calcium. So 2 positive charges from calcium cancels the 2 negative charges, from the 2 NO3. We need to decide if this is solid or not. And so for this, you would need to go to your solubility rules. So go to your reference packet and go to page 3. Page 3, where you have the list of polyatomic ions, and you see the nitrate there, NO3 negative 1, and NO3. NO3 here, first listed in the soluble ionic compound. NO3 makes only soluble compound, no exceptions. So we know that nitrates are always, soluble. So if it's soluble, then you need to write AQ after the AQ, because it's aqueous, which means it's soluble in water, right? Soluble in water. So that's what we call the skeletal equation here, because it's not balanced. If you look carefully, we have 2 NO3 here on the right, and only 1 on the left. So to balance that, we can make it a 2 in front of HNO3, right? But the 2 goes in front of the whole HNO3 to make 2 nitrates on the left, 2 nitrates on the right. These are easy to balance, that's why I'm doing it without writing things. But remember, when you have this kind of reactions where you have polyatomic ions, like the nitrate, the hydroxide, you balance the polyatomic ions, and you will see that if you do that, it will balance very easily. So here I've balanced the nitrate. Now calcium, I have only 1 calcium on the left, 1 calcium on the right. The hydroxide, I have 2 hydroxide on the left. And to balance the hydroxide and the H+, you need to balance the molecules of water. When you have, for each hydroxide, you need 1 H+ to make 1 H2O, right? And here we have 2 OH minus, 2 H+. So those two H+ and 2 OH minus will make 2 molecules of water. And that's how you balance this type of reaction. You want to balance the hydroxide and the H+ with the water, and then balance the polyatomic ions. And here, that's what we do here. We're balancing the polyatomic ion, because we know it combines with H+, so we need to have 2 water molecules. Because you can see here, 2 times 2 is 4 hydrogens on the right. And here we have 2 hydrogens plus 2 hydrogens, it's 4 also on the left. Oxygen, and oxygen from the NO3 doesn't count here because we already balanced it. The oxygens here from water will come from this OH, those 2 OH. So 2 oxygens there, and in water we have 2 oxygens. So if you follow that, it's, those equations are fairly easy to balance, hopefully for you too. And that's it. That's the neutralization reaction of nitric acid when it reacts with calcium hydroxide.